Oops. Okay. Great. So we were discussing quotient rings of polynomial rings, and we stated here that we will prove let f be a field and let f of x be in f of x. What is the statement? Then the quotient ring, then f of x modulo the ideal generated by f of x is a field if and only if f of x is irreducible in f of x. This was the main theorem that we proved, that we stated. We'll prove it today. First, before I prove it, I'll just start with a small thing. With another proposition. It's not a. Yeah, you guys did not see vector spaces. Okay, so let's. So that's a problem. Let f be a field, and let g of x belong to f of x. Let's see. And suppose that g of x has degree bigger or equal to 1. Okay, then. For any h of x in f of x, there exists a unique r of x in f of x such that h of x plus I is equal to r of x plus I, where I is the ideal. Generated by, what did I say, g of x in f of x. Okay? So basically, if you have any polynomial, its residue class, any polynomial can be represented uniquely by a residue class in this quotient of the, what do I say? Unique r of x of degree strictly less than the degree of g, right? Yeah, this is the. Okay. Let's prove this. Really, r of x is the remainder of the Euclidean division of h of x by g of x. For proof, to write h of x as g of x times q of x plus r of x, where degree of r of x is less than degree of g of x. This includes the case that this includes the case r of x is 0, because degree of 0 I assume it to be minus infinity. Okay, so minus infinity is less than this. Then what? Yes. Then h of x plus I is equal to g of x, q of x plus r of x plus I. Now, g of x, q of x, does it belong to I or not? I is the ideal generated by g of x. So does g of x, q of x belong to I? Yes. So what is g of x, q of x plus I? This is just plus r of x, so just r of x plus I. Agreed? If you reduce modulo I, modulo the ideal I, this will be 0, this will be r of x, and this will be h of x. So h of x plus I. Okay, now uniqueness. Uniqueness is also obvious. Well, this is basically the uniqueness of the remainder. Now suppose r prime of x in f of x is such that degree of r prime is less. I mean, maybe let me write or r of x is 0 just in case. Okay, I mean, it doesn't matter. I mean, I don't want to, yeah, anyways. Is that a degree of g, or r prime of x is 0, and h of x plus I is equal to r prime of x plus I. Then, r of x plus I is equal to r prime of x plus I. Right? Because h of x plus I is r of x plus I. Hence, r minus r prime belongs to I. Hence, r of x minus r prime of x is equal to I. Hence, r of x minus r prime of x belongs to the ideal generated by g of x, which implies that, hence, g of x divides r of x minus r prime of x. Agree or not? Yes or no? Great. Now, the degree of r is less than the degree of g. The degree of r prime is less than the degree of g. When I subtract both, can I exceed the degree of g or not? No. Hence, so therefore, in exchange, there exists. What letter do you want to use? L of x, k of x, let's say, such that g of x is k of x times r of x minus r prime of x. Now, the degree of r minus r prime is strictly less than the degree of g, right? This is clear. What is the claim here, by the way? What should I get to? That r is equal to r prime, right? If I want to show that r is unique, I have to show that r is equal to r prime. Yeah.
You were saying that I is the ideal generated by g of x.
Yes. I wrote this before, right? Or no? Did I write this? Yeah. Okay. So if you want to show the uniqueness of r, you have to show that r is equal to r prime. Now suppose r is different than r prime. Suppose r is different than r prime. What can you say about the degree of this?
It's at least 1.
It's at least 1. Very good. Sorry, it's at least.
Is 0.
It's not minus infinity, right?
So it doesn't.
Yeah. So the degree of g is equal to the degree of k plus this thing. Now, do you see a contradiction or not? see a contradiction? The idea is that can g of x divide a polynomial of strictly smaller degree? This is the idea. Can g of x divide a polynomial of strictly smaller degree except 0? Can 6 divide a number strictly smaller than 6, or a positive number between 0 and 6 that is not 0? Same argument here. Okay? So let's just, is the argument clear or not? Right? Can g of x divide a polynomial of strictly smaller degree if you're in a field, unless it's 0? Everybody, do you see that argument or not? Yeah?
Well, we could say that because F is a field, sure.
Yes.
Domain, therefore R minus
Exactly.
must be
Exactly. Yeah, exactly. Exactly. G of x divides R minus my part. This is wrong here. This should be K of x here. I was puzzled for 2 seconds. I was like, how to do this? Okay. But this is the mistake here, yeah. Okay. Now what can you say with the degree of R minus R prime? If R of x minus R prime of x is non-zero, and since F is a field, then the degree of R minus R prime is equal to the degree of K plus the degree of G. K non-zero, yeah? Then, what can you say here? You contradict the fact, right? You're contradicting the fact that degree of R minus R prime is strictly less than the degree of G. Right or no? You see that? There should be strictly less than the degree of G. Or you know what? Let's keep this 0 here. Ah, that's good. Okay. Then what can you say about the degree of K if you have this here? It must be minus infinity, right? So K must be 0. You guys see that or not? Do you see the argument here? It's an obvious argument, just like we have to write it down. So basically, if g of x divides a polynomial of a smaller degree, then this polynomial must be 0 if you're over an integral domain. Is that clear? That's the idea. That's the idea of the proof. Okay, so there exists k of x such that k of x, g of x are x minus 1 prime of x. No. So this is what g of x divides. Yeah, so if r of x minus, then k of x is different than 0. And since f is a field, degree of g contradiction. Contradiction. Okay? Because the degree of r minus r prime should be less than the degree of g, and this should be less than the degree of g. You see that or not? You guys see this or not? Yes or no? Should I write one more line? Let's write one more line. But the degree of r minus r prime is strictly less than the degree of g. So, contradiction. Hence, R is equal to R prime of x. Okay? This is the idea here. The uniqueness of the remainder. This is the proof, if you will, of the uniqueness of the remainder of a Euclidean division in f of x. Okay? Same argument for z, right? In z, we did the same argument. You realize that or not? It's the same thing. I just replaced numbers by polynomials. And the absolute value by degree. Okay? Again, I'm not going to question now this. So, it's not very important. Now, corollary. One, f is a field. And g of x and f of x has degree 1, has degree n bigger equal to 1, then f of x modulo g of x is equal to, let's see, an xn plus, an xn minus 1 plus a1x plus a0 plus I, as a1 belongs to a0 belongs to f. Right? Take any h of x and reduce it modulo I. You get something of smaller degree, and these are the only possibilities. Basically, reduce something mod p. What do you get? When you reduce something mod p, what are the only possibilities? In integers. Modulo 5, what are the only possible residues? 0, 1, 2, 3, 4. Here, when you reduce modulo g of x and f of x, what are the possible residues? These are all the polynomials of degree of degree at most n minus 1. Okay? 2, if f is finite. Yeah, just a second. Yeah, is there something?
Wouldn't it start at an minus 1 instead? Because
an
also
minus 1, yes. 2. If f is a finite field, if f is finite, then f of x mod g of x is finite and has size. What is the size if f is finite and g of x has degree n? How many, let's say f has size q. How many possibilities do you have for an minus 1? An minus 1 are in f. How many possibilities do you have for these? Q, right? An minus 2, how many possibilities do you have for these? How many possibilities do you have for, how many such polynomials do you have if the coefficient are to belong to a finite set with q elements?
n times degree of n.
Q? Yeah, q to the n? Is that what I want to say? How many choices do you have for q, for a0? Q. How many choices do you have for a1? Q. a2? Q. an minus 1? Q. So it has size. F. The cardinality of f. Yeah. Okay, next term you will see this. This is a f vector space of dimension n. Pretty cool vector space.
We never
Very
saw
important.
that.
Yeah, but usually you see that. Okay. So it's yeah.
Should we explain why the size has like specifically why that size of the field to be n? Because it's like wouldn't you just have like an infinite number of x of like x?
Yes, but the quotient ring you stop at n minus 1.
The coefficients don't need to be
In f.
do they?
They need to be in f. How many choices do you have for f?
Well, yeah, you have n choices here.
Q. Q.
Or q.
You didn't write q.
There are f choices here. Okay, so you have f choices. Okay, how many choices do you have here? F choices. Right? A1 f choices. A2 f choices. An minus 1, how many? F choices.
What is the combination of all of them?
Okay? Great. Now enough with this stuff. Let's give an example to see how it works. Or no, let's prove the theorem. Theorem or example?
Theorem. We did a few examples last time.
Yeah. But the examples are, I feel the examples are more important than theorem. So I'm tempted to do one more. But let's do the theorem. Let's do the theorem.
We can do the examples after.
And then, we'll just continue with the examples. Again, I posted like 2 sheets, right? You saw these? Try to do them. If you do them, you should be fine. Okay? If you do them, you should. They're a bit on the hard side. Some of them are hard. But Yeah, it just, I mean, you see second cheat, I just construct a field with 25 elements, construct a field with 49 elements, construct a field with I don't know how many elements. So this is just should be, or are these two rings isomorphic? I give you a quotient field by an irreducible polynomial, and I give you a quotient field of the same field by a non-irreducible polynomial, and you have to tell me whether they are isomorphic. Clearly they're not. If the polynomial is you're quotienting y is irreducible, then the quotient ring is a field. If it's not irreducible, then the quotient ring is not a field. Boom, 2 lines. Okay, well, not 2 lines, but anyway. Now let's prove the theorem. Theorem. F of x modulo f of x is a field if and only if f of x is irreducible in. Okay. Let's start with the easy one. Or let's do it this way. Okay? What I will do is that by contrapositive, I'll argue by contrapositive. Suppose f of x is not irreducible. Here, of course, like f of x have degree equal. You know why I say that? Just to avoid that f of x is 0 or that f of x is a unit, so I don't get the zeroing. Okay, so suppose f of x is irreducible, then there exists h of x, g of x in f of x such that f of x is g of x, h of x, and the degree of g is strictly less than the degree of f. Right? Of course, still we can assume that doesn't matter really. Degree 1 is irreducible. So degree of g, degree of h is strictly less than degree of f. Why did I say 2? Just so that I don't contradict this equality. Okay? Just so that I don't say, yeah. Okay? Then, let's look at f of x plus I. So let I be the ideal generated by f of x. What is f of x plus I? It is equal to g of x, h of x plus I. What is that? This is a 0 plus I, and this is equal to g of x plus I times h of x plus I. This is the property of the quotient ring, right? Multiplication in the quotient ring. Now, what can I say about g of x plus I and h of x plus I? Are these 0 or not?
No.
G of x is non-zero. G of x plus I is non-zero. It's different than 0 plus I. Why is that? Because the degree of g is less than the degree of f. Right? You see that? G divides and h of x, well, it doesn't matter here. Well, it does actually. Yeah. And h of x is different than 0 plus I. Multiply these two, what do you get?
Wait,
Yeah.
Wait, wouldn't it be h of x plus I?
H of x, yes, sorry, thanks. H of x plus I is different than 0 plus I. Now, you agree that these two are non-zero or not? You agree that these are non-zero? If you have a polynomial of degree strictly smaller than f, then its equivalence class modulo I is non-zero, unless it's a 0 polynomial. You agree or not? And here I assumed already that these are non-zero, because they have degree at least 1. So what can I say then? Then f of x, mod f of x, is not an integral domain. Is not an integral domain. Hence, not a field. Okay? Yep.
But then this assumes big F is finite, right?
Why?
No?
No, why does it assume big F is finite?
Wait, no, it's the other direction.
No. Okay, so if f of x is not irreducible, then the thing is not an integral domain. Not only is it not a field, but it's not an integral domain because you could find a zero divisor. Let's give a small example. Let's say r of x mod x squared. Okay? Small example. What is x times x in this ring? X squared, which is, in this ring, x squared is congruent to 0. Okay? You see that? Is x 0 in this ring? No. Okay? This is the idea. Great. Yes, I'm proving by contrapositive. Yes. Okay, let's prove the other way. I mean, all of this, maybe in your next algebra courses, you'll see a more general framework. Now, suppose f of x is irreducible. I want to show that f of x is a field. F of x mod f of x is a field. How do I do that? Remember, how can we show that z mod nz is a field? Same proof for integers. Yeah.
N is prime.
Sure, you're using something with prime numbers. Very good. Very good. Yeah, yeah.
Not necessarily.
What can we use here? Yeah.
You can say, like, suppose it's not a field, then there are two polynomials such that if you multiply them together, you get back f of x.
Yeah.
This is impossible since it's irreducible.
Sure, you can do that, but I think this is a bit more work. This might be a bit more. This is a bit more work. Yeah, so what you're gonna do, you take two elements that are non-zero, and then you pull back, and then you say, okay, this is my f of x, that is a product of these two. Yeah, could be doable. Could be doable. Could be doable. Yes. I think, well, I mean, I'm saying like without trying. Yeah. I think, yeah, you might be able to do it this way. Or, but what's an easier way, a quicker way? The Euclidean algorithm, right? Yes? You see that? The Euclidean algorithm? Suppose f of x is irreducible. And let g of x and f of x be such that g of x not belonging to I, where I is the ideal generated by f of x. Well, I said it already. So f of x does not divide g. Does not divide g of x. Now, what is the what is the GCD of f and g? What is the GCD of f and g in that case? GCD of f and g, what is it? Again, f is a prime number. Always assume that f is a prime. Exactly. Right? Assume that f is a prime number. If f is a prime number, the GCD of something ng divides, GCD of f and g divides f, and since f of x is irreducible, GCD fx gx is equal to 1, or GCD fx gx is equal to f of x. Now I claim the second one is not possible. Why the second one is not possible? Yes?
F of x does not divide g of x?
Exactly. Since f of x doesn't divide g of x, then GCD f of x, g of x is 1. Hence, what can I find? I can find polynomials u and v. Hence, there exists u of x, v of x, and f of x, such that what? F of x, u of x, plus g of x, v of x is equal to 1. Take this modulo I. What do you get? Plus I is 1 plus I. Now, does f of x, u of x belong to I or not? If I is the ideal generated by f of x. Yes? If I is the ideal generated by f of x, does f of x, u of x, is f of x, u of x a multiple of f of x?
Yes.
When you reduce mod I, what do you get here? 0. So what do you get? You get g of x, v of x plus I is equal to 1 plus I. Oh, wait a minute. This is, you just found an inverse for g, right? So you get that g of x plus I, and it's v of x plus I is equal 1 plus I. So the quoted gx plus I has an inverse. Has a multiplicative inverse. Sorry. Inverse and right? And the only assumption that I had is that g of x plus I is non-zero. So f of x mod f of x is a field. Great. Very nice proof. Very beautiful proof. Unfortunately, you won't have to know it for the final. Sadly. Sadly. No, it's a nice proof. So but I mean, if you want to know it, I can still change it. You know, it's I can still change it.
No, you can't.
I love it.
You're too close to the final.
I just make an announcement. Please add one exercise. Please add one exercise.
You can give us as a, like bonus problems. You don't mind?
For bonus points?
Bonus like in the no bonus no. No. The final is I think I've said to everybody. I'm just worried about 15 points at the final. So 15 points on 70 are the marks that worry me.
Why?
They're not hard, and they're not hard. They're just new things.
But the rest are pretty much hard.
The rest is just very close to the homework, or the same homework, or the notes. So 55 on 70 is like, copy paste, almost copy paste, almost copy paste from homework. I might add one thing, switch things a bit, but there are like 15 marks that are totally new. But that shouldn't be a problem. Yeah. And a multiplicative inverse. Okay, let's give examples here. Let's work with finite fields. Okay. I mean, but the homework grades are really good, actually. Like, the homework grades are actually very good. In general, the homework grades are very good. The midterm grades are very good. So I think the class is doing very well. Actually, though. Seriously. And I'm sure you will do very well in the final. But in general, the class is doing very well.
Does that mean you'll make the course harder for the future generations?
No, I mean I might not teach it next year, but no, it's. But again, I'm not the harshest in grading, I guess. You know, I'm not very harsh in grading. Yeah. So I just make it up by making this stuff a bit harder. I mean, I make it work a lot, but at the end, it's good. I think. Anyways. But yeah, no, the average of the. I think I didn't compute the grades, but I think maybe 40% of the class has 100 on the homework. After I do the modification, maybe more than 40% I would say has 100 on the homework or close to 100, which is very good. Yes.
Is the modification like the point capping?
Yeah,
right?
the point cap. The bonus I'll grade at the end. I will not grade it now.
Ah.
So if I need to grade it, I'll grade it. So if you get an A, I will not grade your bonus. Yeah.
Is that bonus homework just applying to like the homework grade or like?
I mean, I've explained it several times, like how I'll do the calculation. I forgot how.
Yeah, I
how I'll do
forgot
it.
too. So.
Okay, so I mean, I put a post yesterday. I
Oh,
wrote
okay.
how I did it, so
All
please read that. Yeah. Okay, great. Let's do some. Yes, sir.
Do you need to prove for Koshi for the exam? I just don't know.
Like you already said
No.
No,
No need to prove Cauchy.
no, it was so complicated, so thank you, sir.
No need to prove quotient. I mean, I think I've reduced many things, right? I threw out many things, right? So.
Koshi is too hard, it's impossible.
Yeah, it's not an easy one.
We have
Okay,
to
great.
know it, but we don't have to know how to.
Let's example. Construct a field with how many elements you need. Let's see how many elements you need.
37.
Let's say with
37?
37. There's only one field of order 37. What is it? Z mod 37Z.
Yes.
Now let's construct a field with 8 elements. Yeah, so sure. A field with 8 elements. Okay. How do you want to start with that? What is the base field you want to start with? You want to use that theorem, right? F of x mod g of x. Okay? So what's your f of x? What's a good candidate for f of x? What is 8? 8 is 2 to the power 3. Now if you have a finite field, if f is finite and this has degree n, then this has f to the n many elements, right? Now, how can you match these f and q and 3? What's one way of doing that? F is equal to what?
F2.
The size of, yeah, f is equal to
Z mod
f2 and n is equal to 3. Okay? So let f2 be the field with 2 elements. This is one way, it's not the only way. By the way, can you start with z mod 8z or not?
No,
No,
it has zero.
because z mod 8z is not a
Field.
field. Okay? Let f2 be the field with 2 elements. I need to find an irreducible polynomial of what degree?
3.
Everybody, of degree what? Okay, so if I have a polynomial of degree 3, it is irreducible if and only if it has no roots. How do I construct that in f2? You want a polynomial of degree 3 that has no roots. In general, like there's no way, just think. So what do you need the constant term to be? Can the constant term be 0?
No.
If the constant term is 0, then 0 is a root. You agree? If you have x cubed plus x, then 0 is a root. Yeah? Great. So what if the constant term is not 0, what must it be? 1. Great. So let's add a 1 here. And you know you have an x cubed here. Okay. 0, so you need something in the middle, right? Is this irreducible? Is x cubed plus 1 is irreducible? 0 plus 1 is 1. 1 plus 1 is 0. So that's not irreducible. You need to add something. What do you need to add?
X.
Throw in something. Anyone, throw in something.
X cubed? No,
X cubed is already there.
X squared.
Plus x squared. That's right, x squared.
Okay, X. Yes.
Is this polynomial irreducible? Does it have any roots? Plug in 0, what do you get? 1. Plug in 1, what do you get?
3, but 1.
1 plus 1 plus 1 is equal to 1. So does this polynomial have a root? No. Let f of x be equal to x cubed plus x squared plus 1. Then f has no roots. F of x has no roots in f2 since f of 0 is equal to 1 and f of 1 is equal to 1. Agree or not? Now since f of x has degree 3, f of x has degree 3, what can I say? 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 Then f of x is irreducible. In f of x. And hence f of x modulo f of x is a field with 2 cube elements. Okay? What time? Do I have a lot of time left?
It's 11:17.
I have, okay, so I have time.
Could be nice.
Now, another question. Is f of x modulo x squared, is f2 of x modulo x cubed, sorry, isomorphic to this field or not?
No.
Take f2 of x modulo x cubed. Is it isomorphic to this one? F2 of x modulo x cubed. Is it isomorphic to this one? Anyone can help me what? Yeah. Exactly. Very good. You'll have something like that, okay? You'll have a question like that. You can expect something. I'm not saying you will have. You can expect something like that. Okay? Yeah. So isomorphic to no. X cubed is not irreducible in f2 of x. So f2 of x mod x cubed is not a field. Okay? The other one is a field. Yes?
How much do we have to justify our answer on the exam? Like if we got
This is
questions.
good for me.
That's good.
This is good for me. Yeah. You don't have to show me how you got your polynomial. Okay? You just have to tell me this polynomial and check it first. Okay? So it's not isomorphic. We do one more? F2 of x. Let's construct a field with 25 elements. Yeah.
Is it possible to make a field of composite size?
Well, what did we check? Very good question. We have a theorem before that any finite field has order p to the m for some prime p and for some m. So the only possible order of finite fields are powers of prime numbers. Right? We saw that theorem, no?
Yes.
Yeah. So can you have a field with 6 elements? Can you have a field with 10 elements? Is 10 the power of a prime number? No. Can you have a field with, I don't know, 12 elements? No. Can you have a field with 25 elements? Yes. Now, in general, it's a bit harder to say that you have a field of p to the n elements. It's a bit harder. Next term, maybe you can see that. But yeah, this is more linear algebra and fields. You will see this next term, maybe, hopefully. Okay? Let's do one more example. Even if I say a bit, I think it's helpful. A bit more than the time, I think it's helpful. Let's see. Construct a field with 25 elements. So what do you start with? 25 is what? 5 squared. So what is, you want to use the theorem of polynomial rings. What polynomial do you start, what coefficient, ring of coefficient do you start with? F5. And what do you need? An irreducible polynomial of degree 2. Okay. How do you check that a polynomial of degree 2 is irreducible? If and only if it has no roots. Now, what are the nicest possible irreducible polynomial of degree 2? If you get x squared minus something, and this x squared doesn't, like, say x squared minus 2 in Q. It doesn't have a root in Q, right? Root 2 is not an element of Q. So what you want is that to get x squared minus something, where this something is not a square in F5. So what can you do here? Write down the elements of F5. 0, 1, 2, 3, 4. And write down the square of each element. What is 0 squared? 0. What is 1 squared? 1. What is 2 squared? What is 2 squared? 4. What is 3 squared? You just copy here. You just look at this. You just flip it. Because 2 is minus 3. So it's going to be the same thing. Okay? Great. Now, if you take x squared plus 2, does it have a root or not? Can you find an element whose square is minus 2?
Which is 3.
Let f of x be equal to x squared minus 3 in F5 of x. Is 3 a squared modulo 5? Can you find an element whose square is 3 in F5? What are the possible squares in F5? 0, 1, and 4. You agree or not? Plug in any number here. Will you get 0? If you plug in any number, will you get 0? No. You see that? Everybody sees that? You see that? Plug in any number in F5. What is 0 squared? Minus 3. Well, 0 squared plus 2 is 2. 1 squared plus 2 is 3. 2 squared plus 2 is 4. Well, it's 1, right? And then, 4 squared plus 2 is, 3 squared plus 2 is 1. 4 squared plus 2 is 3. So you never get 0. You guys see this or not? You see how I did it? I just took the square of all elements, and none of them is equal to 3. So x squared can never be equal to 3. We see that? Yeah? That's it. Hence, let F5 be the field with 5 elements. Yeah, so f of x has no roots in f of x, in f5 in f5, and hence, since f of x has degree 2, f of x is irreducible in f5 of x. Then f5 of x mod f of x is a field with how many elements? X squared plus 2, x squared. Okay. Maybe one more question. That's a nice question. Let me call this field K. Okay? K is a field, so I can apply the whole theory of fields to K. Let K be equal to f5 of x mod x squared plus 2. And let g of y be equal y to the 25 minus 1. So g is a polynomial of degree 25 in this ring, in this new with coefficient in this field of 25 elements. So, like really the coefficient, this polynomial ring has coefficients that are residue classes of polynomials. Slightly complicated. Now, how many roots does g of y have in K?
At least one.
Yeah, sure, 0 and 1, sure. This is a perfect question for the exam, for example. That's a type of a perfect question you can get.
No, we can't get that. Please.
Pardon me? No, this is a perfect question. 2-3 lines of an answer.
Isn't there only one like computational for rings?
Yeah, this is a computational one. Could be AB. Yes, sir.
25 roots.
You have 25 roots. Very good.
Is anything to the power of 25 is the itself, and then minus anything to the power of 24 is the identity, because they all have order divided by 24. Because you take it without 0 and it's a group.
That's right. K without 0 is a group. Every non-zero element is invertible. Agree or not? K is a field, right? K is a field. Agree? So K minus 0 is a group. Right? These are the groups of units of K. Agree or not? Yes or no? You agree that, what is the size? Let's call it K star here. This is groups of unit of K. K star, units of K. How many elements does K star have in that case? It's 25 minus 1. Agree or not? Any non-zero element is invertible. So if you have a field, the group of units is all non-zero elements. How many elements does K star have? 24. Now K star is a group by Lagrange. If A is in K star, A to the 24 is equal to 1. A to the order of the group is equal to the identity of the group. So multiply by A, you get A25 is equal to A. So every element in K star is a root of this polynomial. Moreover, 0 is clearly a root of this polynomial.
So there's 25 roots.
25 roots. And in general, that's how you prove that if you have a field, that's how you prove the existence of a field with 25 elements, for example. You take this one, and notice that the sum of two roots is also, let me not talk about this. Yeah.
Why does it have 25 if it says it only 24?
A to the 24 is 1. A25 is equal to A. So any A in K star is a root of G. Plus, and G of 0 is also 0. So any A in K star is a root. G of 0 is also 0. Hence, how many roots does it have? 25 elements. Hence, any element in K is a root of G. Okay? Any x in K is a root of G. Okay, great. Let's leave because... Oh, by the way, there are like course evaluations. Could you please fill them in? There are course evaluations. I get an email that they haven't been